So I will continue with the structure of a partially ordered set. In short, it is often called a poset. You know that it is a set. It comes in with a relation, usually written like this, where this is a relation on X. It is reflexive. It is transitive. And antisymmetric. Now, the usual picture that one can think of is obviously trying to picture it like this, where you have a set X and you draw a line like this to say that A is less than or equal to B. So you can think of such lines. The antisymmetry says that if you have also a line in this way, then they must be equal. So if they are separate, then there's only line in one direction. The transitivity says that if you have this going to another one, then you obviously have a line like this. So as if you are saying that between the elements there are some kind of paths, one-way paths from one element to another. Obviously, there can be elements which are inaccessible from any others. So this is the rough picture that we are going to have about partially ordered set. Some immediate, you have already seen something called a semilattice. So either a meet semilattice or a joint semilattice. And they were very special cases. So we will try to see why they were special. So to do that, let us take a subset A of X. Obviously, we can call an element X to be an upper bound of A. Can you say what is the most natural way to describe an upper bound? What should be an upper bound? If yes, anyone? So this is my A. What should be an upper bound? If my X is here, how should it be? How should it relate with this A with respect to such picture? Yeah. So okay, let me put a little more light. When I write something like this, I'm inclined to say this, that B is greater than A, right? So C is greater than B. So therefore C is greater than A. So that's the picture that I'm trying to produce. So what should be an upper bound of all the members of A? So that should be an upper bound of A. What should it be? Yes? Okay, so let's give a try. So it means that it is larger, X is larger than every member of A. So that means whenever I take a member from A, U is less than or equal to X. So the picture is like this. So whatever you might take, so it is something like this, right? And if you have the dual side of the story, then you would say it's a lower bound. If again U in A implies that Y is less than or equal. Okay, so it's well, let's extend this. So if it is something like this, then you want to say something like this. Yeah. Obviously, you can collect the all the upper bounds of A. So AU, I will write like this with a U in bold to be the set of all upper bounds. Of A, and A with the this to be the set of all lower bounds. Okay. All right. So let's take up some examples that should, some simple examples is, say, let's take the set of all integers. And this is the usual order. What does it mean? M is less than or equal to N if and only if N minus M is greater than or equal to 0. Okay, the usual order. So what can you say to be the upper bounds of, say, suppose if I take A to be say up to 10. So what is AU? Any idea? Any idea? What is AU?
Could it be 10?
Well, yes, 10 is there, but
Or should it be a set? Oh, yeah,
yes,
it has
it
to
is
be
a
a
set
set.
of all upper bounds. So what should it be? 10? Anything else? Can you say? Anything else? Or is it only 10? Yes, 10 is right. But anything else? Okay, observe. If X is an upper bound, this statement automatically says that if X is an upper bound and X prime is bigger than X, then X prime is also an upper bound. And somehow the dual of this, if Y prime is less than or equal to X, then Y prime is also a lower bound. And this is expected. If you have something big, something bigger than that big is obviously big. So coming back to this, so what is this? What are the things? So everything bigger than 10. So you can write this as X, all integers which are bigger than or equal to 10. And similarly, you can see AL is all integers such that it's less than or equal to 2. Okay, but let's take another set. Suppose if I take the set B, to be all the even integers. So what is the set of all upper bounds of this? And what is the set of all lower bounds of this? Yes, Lian or Ukone? Xander?
So will the upper set of all upper bounds be empty?
Correct. It has to be empty. Why?
The set of all even integers is
Is
infinite.
no. Let us.
Sorry.
Yeah.
If I can take a guess, because any upper bound you could try and impose on it, you could show another number that is bigger than that that still meets the requirements of being an even integer. So it's forever increasing.
Good, good. So suppose if I had an upper bound x, now being an integer, it will be either even or odd. If it is even, then x plus 2 is still an upper bound, but x plus 2 is not. X plus 2 is still an upper bound, which makes the problem. And if x is odd, then x plus 1 is still an upper bound. So, and you can find an integer greater than that. So you see, the moment you try, so that means, so that let's write it down. So suppose if, so what does it mean that x is not an upper bound? Of A. So this means that there exists some u in A which exceeds x. Yeah. So it's just the negation of this formula. So it means that you will always be able to find some u which exceeds that. And that is exactly the principle which you use over here. And what would be BL? What would be BL? Yes? What would be BL?
Would it be 2 or would it be 0?
Well, yes, 2 is there, and therefore next. 2 is there, and therefore anything smaller than 2 is also there. Right? So this example shows that the set of upper bounds or the lower bounds may or may not be empty. Okay, both may be empty, both may not be empty. So let's have another, but something that we observed over here, that the set of upper bounds as if has the smallest upper bound is 10. Or over here also, or in both of these cases, the set of lower bounds have a largest member. Okay. So let's see another example. Let's take the case of rational numbers with its usual order. And let us take the set of all rational numbers such that x squared is less than 2. Is this empty? Is this set empty?
No, sir.
No. Why? Can you give me an element?
A quarter.
Yes, a quarter. Obviously, a quarter is there. I think a much more simpler one is 0 itself is there. Right?
One would also be there, wouldn't it?
One would also be there. Yeah. Okay. So can you give me the set of all upper bounds? And can you give me the set of all lower bounds? Any idea? Such that? Such that?
Such that x squared is less than 2.
If it is less than 2, it cannot be an upper bound.
Oh, sorry. Okay.
Such that x squared what are the possibilities? X squared can be less than 2 or greater than 2 or equal to 2, right? In the order that we have chosen, right? So less than 2 is already in A. So what should be here?
Greater than or equal to 2?
Yes, greater than or equal to 2, but there is a little bit of a problem. For instance, if I take minus 2, then its squared is greater than 2, but obviously I can see that minus 2 is smaller than each one of the members over here in A. So I need to say that a little more and x is positive, right? And similarly over here, x squared greater than or equal to 2 and x is negative. Now it's a little bit, it wants a little bit of doing, and that is for any there exists z prime again in AU such that and similarly for any z in AL that exists z prime again in AL such that z prime is greater than. So the picture is, so if we try to draw, since this is, we usually draw the rational numbers in a line because any two rational numbers are either they are comparable. We don't have the situation like this point, which is not comparable. So if we take 2 over here, then minus 2 is here, somewhere in between is this set. And the set of all upper bounds is somewhere here. The lower bounds is somewhere here. And if you take anything z over here, you'd be able to find a z prime, which is smaller, but still an upper bound. This takes a little bit of a work, but I can leave it to you to check, or you should have seen this in any course in real analysis already if you have done it. But anyway, this is easily, this after a little bit of checking, it can be seen. So what my whole idea over here was to show that the set of all upper bounds or the set of all lower bounds may not have a smallest or a largest member, just as we had in for Z. Okay, and here is an example of that. So naturally the question comes, what happens when the set of all upper bounds have a smallest member? Well, we call it the least upper bound. So the least upper bound of A, this is nothing else but the smallest element of it. So what does it mean? It may exist or it may not exist, as we have seen just now. So if it exists, what does it mean? It means that Z naught, if I might say, this is a member of AU. So this expands to say that U belongs to A implies that U is less than or equal to Z naught. And it is the smallest. This is the first part, and it's the smallest. So this expands to say whenever I take any upper bound, then Z naught is smaller than that. If we expand this a little further, it says whenever U belongs to A and U is less than or equal to Z, so this says for all U in A, if Z is larger than every member of U, then Z naught is less than or equal to Z. Okay. So, and similarly, you can define the greatest lower bound. Of A. And I leave it to you to put the actual description. So describe the formula. Now for some notations, we usually, we know if this may exist or this may not exist. If it exists, then you cannot have two such, because you cannot have two best things just because of that. If Z naught and Z naught prime were both the least upper bound, then both are members of AU. Z naught being the least says Z naught is less than or equal to Z naught prime. Z naught prime is least says Z naught prime is less than or equal to Z naught. So antisymmetry forces that they are equal. So if it exists, it's unique. And in such a case, we usually denote it as a big V like this, and then an A. Or another denotation is sup of A. You will see this usage mostly in analysis books. And similarly over here, it is denoted as a big wedge and A, or inf of A. So now we are ready to say, so what is special about the semilattices that we saw is, so what is a meet semilattice? This is precisely a partially ordered set in which every pair of elements have an infinite. So that means if you take xy in A, this set has an infinite, which we usually write as x and y. This is what possibly most books take it, but I think Zurab meant instead of pair, Zurab meant a little, which I also usually write, I usually take, he meant every finite set. So instead, so this is the definition that I will take. Meets a poset X in which every finite subset has an infinite.
Okay, so I forgot about the empty set, didn't I?
But you had taken that constant. You came in from the monoid.
Ah, so my definition was still correct then.
Yes.
Okay, wonderful.
Yes. Yeah. So and I also like this because why? See, when I take every pair of elements, if I can do it for any 2 elements, I have a smallest. Then I can do it for any 3 elements. I can do it for any 4 elements. So induction says, so for all sets of size 1, 2, 3, 4, or any natural number, I have an infinite. But I cannot still use the word finite because I have not said anything about the empty set. And why do I make such a restriction when a little bit? So coming back then, next question is immediate. What happens if, what is the set of upper bounds of the empty set? So what is this? And what is this? Anyone? Just blindly use this formula. What does it give?
The empty set?
Yes, U belongs to the empty set. You're saying that X is a member of the upper bounds of the empty set, provided for every member of the empty set, it is smaller than or equal to this.
Will it be the set X, the set of upper bounds and lower bounds of the empty set?
Okay, so let's take it again. So X belongs to, this means that, well, this U is bold. Whenever I have this, right? Correct? Now, this is an implication. So it means that this formula has to be true. Now, when can an implication formula be false? So this is a part of the particular logic that we are working in. If we have a proposition P and a proposition Q, then this says that the proposition, so this can be true, both can be true, or it can have only these 4 values, and the valuation for this statement is that this is false only in this case, and in the rest of the cases it is true. Now these two make the most contentious one. It says that we often say that P is a statement, Q is a separate statement. I don't say distinct, but I'm saying another statement. It's a statement in itself. And this is a third statement. P implies Q is a third statement. Okay. Now I'm saying this statement P with respect to this is often called the hypothesis. This is often called the conclusion. So an implication statement is true. So if the hypothesis is false, irrespective of what the consequent is, the implication statement is always true. And this is often called the vacuous implication. So, if there is an upper bound of the empty set, so this statement being true means I have an upper bound of the empty set. That can happen even only if this statement is true. But in this statement, the hypothesis is always false, right? Hypothesis is always false. So this one must be true, right? So it says that X is any member. What does it say about X? So it says that for any member of the partially ordered set, it is an upper bound of the empty set. So therefore, this turns out to be the whole of X. And by similar argument, this turns out to be again the whole of X. Okay. So now I will ask you to say, to find what is this and what is this. Okay. So it is left as a, so you find out for me. Now, the question is if the supremum or the infimum of this exists. So the supremum of this exists if and only if this has the smallest element. And this I know is X. So this means that X has the smallest element. So this means, so the empty set has a supremum if and only if it has a smallest element. And similarly, therefore, you should be able to say that this, the empty set has an infimum if and only if X has a largest element. So in this case, when I'm saying, so a poset X in which every finite subset has an infimum is a neat semilattice. So what is a neat semilattice, therefore? It says that if I take any finite set, I have an infimum, and obviously I have the infimum of the empty set. That means I have a largest element. So that means neat semilattice. It has a largest element, 1, say, and for any x and y in X, I have this, which is the infimum of this set X and Y. And now it is up. So now it's an exercise to check. And this was kind of done. So X is a neat semilattice as here. If and only if X is a commutative and idempotent. No. That's the connection. So between these two structures, one poses it, and this is an important thing. You see, in this case, this definition, the red star, is presenting a neat semilattice as a structure, yes, as a structure, but a little bit different than what Zurab did in the first class or in the second class as a magma, which had an operation. But here it is being defined via a relation, a suitable, a special kind of a relation, right? So this is a little bit different way than in what he proposed. Now this theorem, this last check that I have left for you, it says that these two presentations actually provide the same notion. Sometimes we have such, sometimes we don't have such, so we have distinct presentations. But in this case, it's a nice accident that the notion of a neat semilattice can be presented as a set of axioms using operations, or can be presented as a relation satisfying certain conditions. Okay, so these are two presentations of the same thing. Is it clear up to this point? Any questions? Queries? Leon, Okone, I see Chad or Xander. Okay. If not,
everything is clear.
yes,
so
yes, please.
far, sir.
Yes.
Everything's clear so far, sir.
Okay, thank you. So the next one is, so I come back to the notion of I come back to X of poset. And suppose I take a subset A and I take its lower bounds. So as we have observed, if I have a member over here, say, if I say is here, and y prime is smaller than this, then y prime is also a lower bound. Yeah. So the picture is like this, that you have a set. If you have something and something which is smaller than that, let's say it's like this, then this is also inside. So something like this, yeah, something smaller than a member is also there. Okay, this is a very special. All sets do not have this property. For instance, as we saw, this set of upper bounds in case of where is it? Here, the set of upper bounds of this set A doesn't have this property. 9 is smaller than that, but 9 is not an upper bound anymore. Yeah. So in this case, for instance, sometimes the set of all upper bounds have the property that you have something smaller than that. But I don't say that anything smaller than Z over here. So check over here. There could be a confusion. Here, the upper bounds has the property that the moment you take an element from the upper bound, you can still find a smaller element inside that set of upper bounds. Okay? But I don't say that everything smaller than that is a member of that upper bound set. I said you can find something smaller. Yeah, so here on the other hand, I'm demanding that whenever something is smaller than y, it is still also a member of. So this property seems to be a very nice one. We will see why. So we put in a definition. Subset of this is called a downset. If okay, so you see, obviously, as an example, again, using this vacuousness, can you give me a downset in any poset? Can you give immediately an example of a downset? What's the first downset that comes to your mind? I'm saying yes.
The set of the set of all negative integers.
Okay, good. Provided your x was integers, right? I'm saying yes. Correct. But for any arbitrary poset x, I'm saying this definition should immediately trigger the first example of a downset.
The empty set?
Yes, the empty set. Yes, because this is false. This part is false. So therefore, this statement is true. So the empty set is there. I'll still put it at number 2. What is the first one that should come? Do the most obvious thing.
The lower bound, or the lower bound of the set?
The lower bounds of a set, correct? The lower bounds of a set, yes, you're right. But
the set capital X itself.
Yes.
The set capital X itself.
Yes. Correct. So that's why I thought this could have been the first example. If I replace A by X, this is obviously true. So X is a downset, the empty set is a downset. So AL for any A is a downset. So they are all downsets. Can you give me anything else? Kind of look into this diagram. So suppose if you have X over here, any X, can you think of a downset immediately? Think of the picture that we are trying to construct a set.
The set of all elements less than X.
Good. So which we usually denote it like this. And if I have to be very pedantic and indicate that this is happening in X, I will write it like this. So this is the set of all everything less than or equal to X. So you see there are plenty of downsets. And I will use this notation, the script dn and then X to be the set of all downsets. So these are all members of downsets. So you see, there are many, many members of downset. So this set is not very small, okay? All right, let's see some more. So suppose you have A and B are downsets. What can you say about A intersection B, A union B, A difference B, and so on? Which one of these are downsets? Which one of them are downsets?
I'm not sure about the first two, but I would guess that A without B wouldn't be a downset.
Okay, can you give an example?
I haven't tried to think of an example, but if A and B are downsets, then that means that any element in X that is less than the one that you're comparing to, if it's less than, then it has to be an A or B. So that's telling me that if you try and take away B from A or A from B, then you've now incompleted your downset.
Yes, you're right. Your intuition is right. But a quick example would be from here. Right?
Yeah.
You take any subset of B, say from 6. So that's your, okay, you take this one and take B to be a subset of this. A minus B, you can see, is this. I'm sorry. I'm speaking something nonsense. But yes, you can take an example. So provide an example from, say, Z or whatever. Okay, yes, you're right. What about these two? Let's try. So suppose I have this. What does it mean? What does this mean? This obviously means X is in A and because both of them are true, and you have told me that this was always there, right? So now you are telling me that A and B are downsets. So what does this therefore tell me?
That x prime is an element of A. I'm not sure whether it would be A and B or A or B.
It's A and, intersection means and, right?
Yeah, yeah.
Right? So this means that X prime is an A intersection. Right? Yeah? Clear?
If
Yeah.
I can ask, how would it be possible that A and B aren't the same set?
Well, they can be. But then A intersection B will be A. If A and B are the same sets, A, say, then A intersection B is A. There's nothing more to prove.
So I suppose more what I'm asking is, so maybe I'm misunderstanding the parameters that you would have on the downset, meaning I can't see how you could construct an A and a B on X such that A and B aren't the same set.
Okay. So let's take an example. So I have Z. I have as a downset, and then I have both are downsets, right? You told me.
Okay, yes, okay, I see now how I was thinking wrong.
Okay. Or
Thank you.
if you take any set X. So let me not. So let me take it another. So any set X, and you look into its power set. Obviously, you know by now that it is a poset, and you take all the subsets of A, and you take all the subsets of B. So what am I doing? So here is my set X. So here are the two sets that I have taken. Here is the another one. So one downset has all the subsets of this. Yeah, all the subsets of B. And the other one has all the subsets of A. So what will be in the intersection? Well, the intersection should have all the subsets of this. So all the subsets of this should be over here because they are less than both A and B, right? So you can see there are several instances of this. Already tells us, these examples tell us that the number of downsets of a poset, there are at least as many downsets as X, right? As the members of X, right? So do you get, is your doubt now cleared?
Yeah, I understand. I was thinking too strongly on the right side of that element statement as to what the downset was. So yeah, I wasn't thinking about how the downset kind of like decides how you define the downset, not really the statement of the downset itself.
Yes. This statement is the definition of a downset. So it has the first part is the hypothesis. The second part is the consequent. But I'm not speaking about this, neither I'm speaking about this, but I'm speaking about this third proposal which says whenever this hypothesis happens, then this consequent happens. All right. So I'm actually telling a property of the, so I'm kind of saying it is a set which has the following property. Whenever you have an element inside the set, anything smaller than that element is also in that subset. So it's a property of that set that I'm specifying by this implication statement, right?
With this in mind, would it be correct to say that the downset of A and B would be the smaller of the two sets, and the downset of A or B would be the bigger of the two sets? So, for the example that you gave with 7 and 5, would the downset for this 7 set and this 5 set be the 5 set, and then 7 or 5 be the 7 set?
Yes, but then we have to first show that A union B is also a downset. Is it true? But to do that, you should observe that this AND can be easily replaced by OR, right? So observe that AND can be replaced by OR, and that would tell us, so that's also another exercise. So give me, and so actually what I'll propose as an exercise, I'll write it down. Also observe that there is nothing special about these two things. Why two? If you have three, the same proposition, the same proof kind of would work. 4, 5, why 4, 5? If you have any, so if you have AIs, so if for I in any set, then so this is the proposition that you should prove. And then I leave you with an example or with a question. Yeah, can you find the smallest non-empty downsets? What are they? And if you can find them, then obviously the next question is, if you give me any downset, what is the relation of this downset with those smallest ones? So that's the next two things with which we will start next time. And I believe I should stop now, right?
No, it's a 2-hour lecture, Partha.
Oh, it's a 2-hour lecture. Okay. Okay, then I can continue. Yes. So, can you find the smallest downsets? What do you think should be the smallest downsets? So let's bang on that. You told me that when you came to this one, you told me that you will take all the things which are below this Fine. That gives rise to this. So can you probe along this line a little further to see what is the smallest downset? What should be the smallest downset?
Could it be
No. I think my statement is not right. How should I say this? Let me make it a little more clearer. So obviously, when we are looking into subsets, so obviously we should consider, so if A and B are downsets and A is a subset of B, then we should say that A is smaller than B, and so on, right? So I'm trying to say, so if you see, if you look into the powered set, yeah, how does this powered set look like? Well, at the bottom there is this empty set, and on the top there is this set X. Now this X is going to mix with, so let me put it in another color. Yeah. So that this X, and you shouldn't confuse it with the previous X. Okay, now in between you have many subsets, but the next level above the empty set you have the singletons, right? So everything is like this. Then you have so if you had this as your singleton A, this as your singleton B, then you club these two to get hold of A union B, which is this. Then you have all these double things. Then you club this with this. If this is singleton C, you club it with this to get your A, B, C. Observe the smallest of the sets which contain both A and B is this. So this is actually the supremum of the singleton A and the singleton B. This is the supremum of the pair A, B, and C, and so on, right? And you go up and up like this. So I meant the word smallest to kind of say, refer to elements like this. Now let's see if I can make it a little more formal. So what is it that I'm saying? So you see, this is a non-empty set, but if you take any subset which is smaller than any such thing, it has to be the empty set. So often such sets are called atoms. So an atom in a poset is an element such that if you have any, yes, in a poset with the empty set, with the smallest element, with the smallest element 0, say, we use 0 to denote the smallest element of this. is an element such that for anything which is less than or equal to A, it must be the smallest or it must be A itself. So see over here, it means that there's nothing non-trivial in between an atom and the smallest element. So obviously you can correlate the meaning. If you remember, Dalton's definition of an atom is the smallest indestructible element, right? Well, by that time he didn't know about the other smaller elements. So at that time he called that an atom. So it's something like that. So you cannot further break it, right? So that's an atom. Yeah. So my question to be proper is, does have atoms? You should ask the first question, is it a poset? Yes. We have already seen that this makes it a poset because this relationship of being a subset is obviously, we know it's reflexive, antisymmetric, and transitive. And does it have a smallest element? You have already shown that the empty set is therefore the smallest down set, and the whole set X is therefore the largest down set. So we have the smallest and the largest. So then we are in a proper place to ask, does the downsets of X have atoms? Can you think? I bring you back to this screen, to this page where you thought about these examples. So now you should be able to think. Does it have atoms?
I would imagine it would have atoms. It doesn't necessarily only consist of atoms, but it has to have them.
Yes, then what should they be?
Well,
Any idea? Leon, Okone, or Xander? Okay, how should one go about this? So let's see. Let's take the case of sets. How the hell should one go about finding an atom in this? I take a subset, then I throw away one element from it, and I check whether it is the empty set or not. No, it's still not the empty. I throw away another one. I throw away, if I can, another one, and I continue. Well, obviously I'm thinking, so I have the liberty of continuing this transfinitely as much as I wish. So then I kind of have a belief that, well, if I have only one element in that set, I cannot any further throw it away and have a subset, which will still be non-empty.
could you say that an atom is the power, an atom is the power set of the empty set in itself.
If you, in general, the power set of the empty set is 1, so possibly, yes, singleton. And you wanted to say that the power set of the empty set, so those are the precisely those elements or those things which are in one-to-one correspondence with the power set of the empty set. Possibly you wanted to say that. But then if you bring in the power set, the problem is, see, when you're looking into the power set, you're taking all subsets, right? Now you are working with not a set only. You have a set coupled with a relation. So you have an extra structure there. And so just only subsets should not be of concern. So that relation must also, otherwise, if we took only subsets, then we are not speaking something about that structure, right? So it should be, so power set is a very complicated notion from this point of view. Yeah, I don't know. Maybe it could be, but just looking at it from collecting a few elements, I don't think that should. And then you are going via power set of the empty set. So that's another route. Maybe that's not the right way. So that's what I was trying to think. How the hell do you make an atom? The only way is you make it smaller. In sets, it's quite simple. You just throw away elements and you make it smaller. And then you come to the realization that singletons should be 1, and then you prove it further. So now over here, how the hell can you make things smaller? Observe, the moment you have taken something in, you cannot throw away anything smaller than that. The downset automatically takes all of it in its way. So from a downset, what are the things that you can readily dispose to make it smaller? So see, the idea is things below something already in that downset. So if you have a downset, things below are not the things to be thrown away. They cannot be thrown away because the moment you throw it out, the downset itself breaks. Okay? So some other thing has to be, if you have to make it smaller, some other thing has to be thrown. What is it? So you can therefore imagine that if you had something like this x prime was also in your downset, then you cannot throw away x prime or x to make it smaller, right? So on the flip side of it is, if you throw away x prime, you will throw away all of these things, will go out, if you have to maintain the downset structure.
Well, what if you make your downset the intersection of all downsets? Wouldn't you then, or sorry, yeah, or rather, yeah, make it the intersection of all downsets that doesn't lead to you getting the empty set?
So, okay, the idea then you're trying to say is
get the smallest downset that isn't the empty set.
Okay, so yes, so you're trying to tell me that, well, what is this? This is the intersection of all the sets that was above it. So you're trying to say that you take down set S and you're trying to take all the down sets T which are bigger than S, and you're trying to take the intersection of this, right? But then this is obviously S, because S itself is over here. This is obviously S. Yes, S is the intersection of everything which is above it. You can actually make this proper. One has to be a little more careful asserting this equality then. But okay. But the problem is here you're starting from a downset, and I don't know whether this downset is still the atom or not. So okay, let's have another look. So you see, you have a downset. So how does the picture look like? So if I think of things, so if something is there, anything below it is always there. So it contains, now let me draw it in another color. So it contains everything which is below it. So all of it is, should I put it in another color, say, like this. So everything which is below it is there. Now, if I had something bigger than this, if this was there, if this is bigger, and I said that this was also in the downset, then I actually meant that this will also be there. Right? But if I can have something bigger than it, but that is no more in the downset. So that means there is something big. So I can have something similar to like this. Yeah. So all such things like this constitute my downset S. So all of these is my collection S. All of these things. So obviously, if you have to make it smaller, you cannot drop just this one. The moment you drop this, this whole chunk gets thrown out. Obviously, it will make it smaller. Yeah. So now think. How, so if you drop one of them, if this whole chunk drops out, then not only this whole piece will actually drop out. Okay. This whole piece will drop out. So can you see now what should be the smallest downset? So to make it non-trivial, so let me pose the question like this. So S is a downset and it is non-empty, I said. So I said it's non-empty, so there is an X in S. So then can you say what is the smallest? Any idea?
It would be your set of atoms, wouldn't it?
Yes, but any idea? What should be the smallest thing? Okay, all right. So let's see. So if you told me that X is this and X prime is less than or equal to X, then X prime is also in S, right? Correct? Because that's what a downset is. Correct? So for each X in S, this one is already a subset of S. Right? And then I'll fall back on this exercise, which I will expect you to complete. So then this will say that therefore the union this will be a subset of this. This is just a set theoretical thing. Okay? But I'm saying this is just exactly equal to this. Why? Because if I take any P in S, then as I've already shown, so therefore so it immediately tells me that each down set is a union of such things. It's the union of such things. And in fact, this therefore tells me, so therefore, now let's see. So suppose if I have a down set S is smaller than some such thing like this. What does this mean? So this means that for any S in S, S is less than or equal to X. So this means that X is an upper bound of S. X is an upper bound of S. So do you see now that these two results should tell me, so these two results should indicate that these are the atoms. Yeah. So again, it's a little bit of a gap over here. So the end story from this is that your downsets are built up from these things, which are often called the principal downsets or the atoms or whatever. So these are the principal downsets. And this therefore tells us immediately that yeah. So therefore I have immediately something. And this leads us to one observation, that if I start off with any poset, I don't know how that poset looks like. It may have a smallest element, it may not have a smallest element. So it may be any poset. And I look into its downsets. Now this downset seemingly is, as we have seen already, this has a smallest, this is also a poset. This has a smallest element. Where does it go? The empty set. This is the largest element, the whole set. This exercise tells us that it has all possible meets. So it has infima for all possible subsets. It has suprema for all possible subsets. So it is the best that we can think of, right? Every possible subsets of downsets have their infima, suprema, so it's don't have to bother. Such things are often, we'll come to it, such things are often called complete. And I can say that there is a very nice map. So shall I write it like this? So as if I'm filling in the blank. So this blank space is being filled in by this X. So this is a nice map which takes X to the downset of X, the principal downset containing X. Furthermore, this tells us, this 3 tells us is injective and ordered result. Preserve. So, but this one has another nicety. So what is it? So I'll give an indication of this proof. We have already shown that this is injective and ordered preserving. But now suppose, assume that Z is any poset in which the suprema or infima of any subset exists. So some such thing like my downsets. Okay. So I have this. And I'm saying that F is order preserving. So what do I mean by that? If X is less than or equal to X prime, then Fx is less than or equal to Fx prime. Okay? This tells me that there exists a unique So then there exists a unique function which preserves order and if star composed this map. And this is the theorem. This is a very nice property. So this I shall write it as a theorem. And as a, what about the proof? So I need to take it is, which is order preserving. What do? I need to say, where does this S go? But remember, this S is a join of this. Right? So in many of these cases, the function f star is exactly what it should be. If you analyze the situation, because this is this, I need f star to, so I need f star of this, of the downset, the principal downset of x to be f of x. So what do? And I need it to be order preserving. Not only order preserving, it is, sorry, we call it sup preserving. Suprema preserve. Yeah. So it is going to preserve this suprema. So this is the suprema here. Then it must go to the suprema. So the suprema of this must be preserved. So where should it go? So it should go, therefore, to the suprema. So that must be the map. And then one needs to check whether all of this matches. There are many caveats here, which I did jump. But let me come to those things. So what is this actually saying? It is saying a lot about it. So if we have a poset, we are actually, what are we doing? We are embedding it. So injective. The fact that it is injective, the injective means if you agree to consider the downsets of x, if you agree to identify this image of this, right, then we can kind of think of x being injected, of being sitting inside this bigger poset. So we have kind of extended this to this bigger poset. What's the condition of this? That means if I had a relation like this in x, the same relation holds in down of x, okay, in that extension. Not only that, I'm also demanding that if I had something like this, okay, if I had for any subset if I had a supremum like this, then the same thing is still true in down of X. But I have something more. I could have a subset over here which doesn't have a supremum. But what have I done by this procedure is to plug in this supremum of such subsets. Okay, so that's what I have done. So kind of there were certain gaps, certain incompletions within that poset with respect to certain subsets. There certain suprema might not have existed, but when I embed it inside down X, I see that I can find its suprema inside that down X. Okay, so that's the first thing. That's exactly the essence of this equation 1. Right? This is exactly the essence of this equation. It says that certain suprema may not have existed within X, but it now exists within that X. And then the fact that I said that this is preserves disorder and so on and so forth is essentially the whole story picture over here. But this one has something more. It kind of says it is the best way that I can make these incompletions, that I can remove these incompletions. Whatever. Now, how do I match this best way? One way could be, suppose if I had anything, any such Z, which was, so what I'm saying is, suppose if it were possible to put any such Z like this, is it possible to have a Z which is also having all possible joints and all possible suprema and all possible infima containing X? The answer is no. The answer says, this one says, that then you can actually also put the whole of down X inside it. So it kind of says that this is the smallest way, how you can approximate this X by completing all those suprema or infima. So in a sense, this is the best lattice. This is the best partially ordered set that you can get out of this scenario. Now for some definitions. Lattice. Well, this is a poset in which every finite subset has a suprema and an infima. A complete lattice a poset in which every subset has a suprema and an infima. So what we said was, so this can be shortened to saying that down X is a complete lattice in which x sets x, any poset x, for any poset x, down x is a complete lattice in which this is x is embedded. And if you have any complete lattice, and if this is F is order preserving. No, I was a little careless here. It should be sup preserving. And F is only a sup preserving map. So it is, what do I mean by this? That means if you have a subset S of X such that the supremum exists, such that the supremum of S exists, and then F of the supremum of S is this. Okay, so if it is a suprema preserving map, now obviously you can see this in particular says that if it is such maps are obviously order preserving, because if you take when you are saying if you take a 2-point set, its suprema is actually this, the join. So it means so whenever this join exists, then it preserves those joins. So that's the idea over here. And then it says whenever you have a complete lattice and a map which preserves suprema, then you can have a unique homomorphism. From homomorphism means a function over here between complete lattices which preserve the join only. Remember, only suprema preserving map, which makes this diagram to commute. That means this is the best way in which we can include the poset X inside this lattice. There are several gaps. I hope you should be able to figure them out. In the next class, we will start from those gaps and doubts. And then we will kind of see an extension of this. Before I finish, I want to say another thing. So from the next time, you can get yourself familiarized with this. So I will stop speaking about suprema and infima. You see, the picture is the dual kind of, if you replace greater than or equal to by less than or equal to. Well, the idea is already when you studied relations. So when you consider a poset like this, then you already have its opposite poset. Which we will write like this. So here X is less than or equal to Y, or we can even write to indicate this it is opposite. We can write like this. So X is less than in op relation. This means that Y is less than or equal to X. The analog is, suppose if you have a relation, then you have the relation Yx from B cross A such that XY is in rho. right? So it's exactly the same thing what we are doing over here. We are taking the opposite relation of this. Yeah, so that's this one. So this is also a poset. The supremum over here, we can define the suprema infima. So we can define the suprema infima over here. So the suprema in the opposite poset is nothing else but the infima in the actual poset. So that halves our statements, and there are also some gaps in between, which we shall start from there. My whole goal was for today's lecture was to show that although we start off with an arbitrary poset, somehow we can complete it and bring it back to a very, very nice with inside a poset with very nice properties as far as the order structure is concerned. And this nice poset, we will look into it much more closely. And this nice poset, we will see this kind of an extension business in many places, in several places in mathematics. The idea of extensions is actually to provide much more insight about the original poset or the original structure, right? So we often try to find such completions. See over here, the incompletions or the imperfections was the non-existence of suprema. Suprema may not exist, so we wanted to plug in those holes. But remember, when we start plugging in those holes, then we have to keep in mind that we were in an ordered set. So if we plug in a hole of a smaller set, then it should also have some connection with the whole with the suprema of smaller subsets, right? So we cannot just do it arbitrarily. It has to be very coherently done. And with very large posets, to do this coherently is almost something which requires a fascinating work, right? And that work is somehow being done by this masterpiece of this map, which is this downset map. It immediately does it. So with that, I'll stop.